Okay, this is our second video of the day, and now we're moving on to part 2, where we're solving some application problems that have something to do with quadratic equations. So remember the other day when we were doing the other story problems, they had something to do with linear equations. So now we're going to solve more story problems that have to do with quadratic equations. And a lot of times these problems involve formulas, so geometry formulas like the Pythagorean theorem, or areas, perimeters, volumes, and so on. And we're going to be using a graphing calculator for part of this video, so hopefully you have that with you. Okay, you may not want to write down this problem word for word. I don't know, some of you probably do, and maybe some of you don't. So at least jot down the important information so that when you look back at your notes, things make sense. Okay, so we have a box with volume 7,500 cubic centimeters that is to be formed from a sheet of metal whose length is twice the width. Equal size squares measuring 10 centimeters on a side are to be cut from the corners of the metal sheet in order to form the box. What are the dimensions of the original piece of metal? So the original piece of metal is a rectangle. So I'm going to go ahead and draw a rectangular piece of metal. And we don't know the dimensions, so let's just go ahead and use some variables. So we are told that the length is twice the width. So what if we use W for the width? Then the length would be 2W. So what happens is that little squares are cut from the corners. So imagine cutting those squares away. And then what you're going to do is you're going to fold here on that dotted line and here on that dotted line and here and here. And so you're folding up the little sides and that gives you a box. So picture yourself doing that. You could even try that with a piece of paper. So once you fold up those sides, you have this box. So let's make a little sketch. And the box is open top. There's no top on the box, just the four sides and the bottom. So let's go ahead and label the box with its dimensions. So we know that the little squares are 10 centimeters by 10 centimeters. So that means that this dimension right here is 2W minus 10, because it used to be 2W, but we subtracted 10 over here and 10 over here. So we can label that 2W minus 10. And then this dimension right here is going to be W minus 20. Oops, did you see what I did? What should I have done back there? Not 2W minus 10, but 2W minus 20. Sorry about that. I meant to say 20. Okay, back to the other one. This one right here, the green one, is going to be W minus 20 because the whole thing was W. We subtracted 10 here and 10 here. So we'll label that. And then the height of the box is just going to be 10 because that's just the amount we cut from the corner, and that's the height of the section that we fold up. So now we know the length, width, and height of the box. And I'm sure you recall from geometry that volume equals length times width times height for a rectangular solid. And we're told that the volume is 7,500 cubic centimeters. So we can write the equation 7,500 equals 2W minus 20 times W minus 20 times 10. So now we have our equation to solve for W. Let's divide both sides of the equation by 10, and we have 750 equals 2W minus 20 times W minus 20. So then what we need to do is go ahead and multiply using the FOIL method, multiply these two together, and that's going to give us 2W squared for the first. The outside is negative 40W and the inside is negative 20W, so altogether negative 60W. And then the last would be plus 400 minus 20 times minus 20, and that equals 750. Okay, let's subtract 750 from both sides, and we have 2W squared minus 60W minus 350 equals 0. And then let's divide both sides by 2. So we have w squared minus 30w minus 175 equals 0. Now, I'm really hoping that this equation is factorable, and so let's try a few things. Let's see if we can find two numbers that multiply to give us 175 and have a difference of 30. Okay, it turns out that 35 times 5 is 175, so we have w minus 35 times w plus 5. And then we set each factor equal to 0. W minus 35 equals 0, or w plus 5 equals 0. And then we can solve each one. W equals 35, or w equals negative 5. Now, think about the situation. W was the width of the piece of metal. There's no way for it to be negative. That doesn't make sense. So we eliminate that extraneous answer. W equals 35 could make sense. Let's go back to the question. What are the dimensions of the original piece of metal? The original piece of metal was w by 2w, so then the dimensions would be w is 35 centimeters, and 2w is 70 centimeters. Now let's just do a check. When we cut the corners, the dimensions of the box are going to be, let's see, w minus 20 is going to be 15, and 2w minus 20 is going to be 50, and then the third dimension is 10, and 15 times 50 times 10 is 7,500, so it checks. Okay, let's go on to the next one. So I'm just going to go ahead and sketch a right triangle. The longer leg is 10 meters shorter than twice the length of the shorter leg. So let's go ahead and label the shorter leg with an x. So 10 shorter than twice that would be 2x minus 10 for the longer leg. And the hypotenuse is 20 meters longer than the longer leg. So if we add 20 to the longer leg, we get 2x plus 10. So our goal is to find the lengths of the sides. So we're going to want to find x. And what's the formula that comes to mind when you're thinking about a right triangle and you know the sides? Hopefully that's the Pythagorean theorem. So let's go ahead and use the Pythagorean theorem. We have x squared plus the quantity 2x minus 10 squared equals the quantity 2x plus 10 squared. So when we square those quantities, we need to use the FOIL method. So I'm just writing it out so that I don't make a mistake on that. Okay, so we have x squared plus, and then when we FOIL the first set of binomials, we get 4x squared minus 40x plus 100. And then on the other side, when we use the FOIL method, we get 4x squared plus 40x plus 100. So let's get all of our terms over to the left. So we're going to subtract 4x squared from both sides, which actually just cancels it. And we're going to subtract 100 from both sides, which just cancels it. And we're going to subtract 40 from both sides. So we have x squared minus 80x equals 0. Okay, we can factor this by factoring out the greatest common factor of x from both terms. So we have x times x minus 80 equals 0. So that would give us x equals 0 or x equals 80 when we set each factor equal to 0 and solve each one. Now, it doesn't make sense for the length of a side of a triangle to be 0, so that answer is extraneous. And then let's check x equals 80 and see if it makes sense. So that means that the short leg would be 80, and 2 times 80 minus 10 would be 150. And 2 times 80 plus 10 would be 170. And if you check those in the Pythagorean theorem, 80 squared plus 150 squared equals 170 squared. Yes, that actually works. So let's go back to the question. Find the lengths of the sides. So they are 80 meters, 150 meters, and 170 meters. Okay. We're going to move on to a couple more problems, and each of these problems I think we're going to end up using our graphing calculator at some point. Number 6. If a projectile is shot upward from the ground with an initial velocity of 73.5 meters per second, neglecting air resistance, its height in meters above the ground t seconds after the projection is given by, so this equation is the height of the projectile. S of t stands for the height at time t. There are two parts. After how many seconds will the projectile be 100 meters above the ground? So 100 meters above the ground is the height at that moment. So let's put that in for S of t. So we have 100 equals negative 4.9 t squared plus 73.5 t. Okay, so there's our quadratic equation. We're going to solve it for t. The numbers are not very user-friendly, so I think for this particular problem it makes sense to use the quadratic formula, use a calculator, and approximate. So sometimes approximating is just the most logical thing to do, especially when it comes to application problems. So generally I'm going to give you directions. When is approximating okay? When is it not okay? For this problem, let's say it's okay. So what we need to do is get all of our terms over to one side. 4.9 t squared minus 73.5 t plus 100 equals 0. And then using the quadratic formula, we have t equals the opposite of b over 2a plus or minus the square root of b squared. Make sure you have parentheses around your negative number before you square it, or else it's not going to work out to be the right sign. Minus 4 times a times c over 2a. Now I think everybody should practice putting that in a calculator to make sure that you can get it in there correctly and get the right decimal values. So I'm going to go ahead and find those decimal values and then jot them down. Okay, so when I put this into my calculator, I got two different times, 1.5 seconds and 13.5 seconds. These are both approximate. And if you visualize, I was trying to say envision and visualize at the same time. If you visualize the situation here, here's a graph. So the projectile starts at the ground level at time 0. It goes up, it comes back down. This is time. This is height. So let's say that this height right here is 100. It's going to hit that height twice, once on the way up and once on the way down. So that's why we have 2 times. Okay, let's move on to the second part of the problem. How long will it take for the projectile to return to the ground? Okay, the ground is going to be a height of 0. So we're going to put 0 in for the height. So it's like the first part, except we have 0 equals negative 4.9 t squared plus 73.5 t. Okay, we could actually factor a t out of both terms. 0 equals t times negative 4.9 t plus 73.5, and then set each factor equal to 0. So we get t equals 0, and we get negative 4.9 t plus 73.5 equals 0. So t equals 0 would be the moment when it starts. So we don't want that time, we want the other time. Let's subtract 73.5 from both sides, and then divide both sides by negative 4.9. And let's see what that is. 73.5 divided by 4.9 is 15. So that tells us that at time 15 seconds, it has reached the ground again. Okay, let's see what we have in store for the final problem. So this problem has an equation S of x, which represents the sales of SUVs from 1990 to 2001. S is the sales in millions, and x equals 0 is the year 1990, x equals 1 is the year 1991, etc. So we have 2 parts again, and we're going to use a graphing calculator to solve this one. It says use the model, and remember the model is the equation. So when you see the word model, you think use the equation to determine sales in the year 2000 and the year 2001. Compare the results to the actual figures of 3.6 million and 3.7 million. So we're finding S of, let's see, the year 2000 would be x equals 10, since the year 1990 was x equals 0, and the year 2001 would be x equals 11. So we're finding S of 10 by substituting 10 into the equation for x. And then we're finding S of 11 by doing the same thing, substituting 11 into the equation for x. So just grab your calculator and do those two computations, and we'll see what we get. Okay, so I got that the sales in the year 10, which is the year 2000, were approximately 3.627 million. And if we compare that to the actual figure of 3.6, I would say that's pretty close. And then for the year 2001, where t equals 11, I got 4.087, and the actual was 3.7 million. So our value that we got from the model is too high. Remember, the model is just using a formula to estimate. It's not necessarily always going to be correct. Oops, how about if I put another 0 or another O in my 2? There we go. Okay, let me show you a different way to calculate those values. So we're going to grab a calculator, the graphing calculator, and we're going to go into the y equals menu, and we're going to type our function s of x in there. So you see I've already typed it in. And then we're going to go into the table set menu, which is second window, and change it so that it says independent ask. And then we go into the table, which is second graph. I'm just going to clear what I have here already, so it's not in the way. Yours may be clear already. Okay, so we're in the table. We type in 10, we press enter, and it computes the value for us. We type in 11, we press enter, and it computes the value for us. So this is a really great way to compute values if you have a lot of values to compute, or if you have just a complicated expression. Okay, let's go back and finish the problem. So it says, according to the model, in what year did sales reach 3 million? Okay, so that means we want 3 for S. So we have the equation 3 equals 0.016x squared plus 0.124x plus 0.787. Now a person could use the quadratic formula and solve that, and that would work, but what I'm going to do is use the graphing calculator and look at a graph of the function and see where the graph has a height of 3. Okay, so once again, here's my calculator. We already have the function typed in there. We need to set a good window. So we press window, and then the x values are the years. So I'm going to go from year 0 to year 20. And then the y values are the sales. I'm going to go from sales of 0 to sales of, let's say, 7. I don't know how high it really needs to go. And let's take a look at the graph. So we're seeing part of a parabola there. And the question was, in what year did the sales reach 3 million? So what we can do is go back into the y equals menu, go down to y2, type in a 3, and that's going to give us a horizontal line at a height of 3. So you see our point of intersection of our curve and our line is going to be the point where the sales were 3 million. So what I'm going to do is press trace. That makes the cursor appear, and then we can move the cursor closer to that point. We can estimate the point. It's around x equals 8, and x equals 8 would have been the year 2000, what would it be? Let's see, 1998. A more accurate way to get the intersection point is to go into the calculate menu. We press second trace, and then we go down to choice 5, intersect. Put the cursor on the first curve, press enter. Put the cursor on the second curve, press enter, and put the cursor close to the intersection point and press enter, and it gives us about 8.5. So again, if we're just rounding to the nearest whole year, we would say that is somewhere in the year 1998. Okay, so we've gone through a lot of problems today. Here's our assignment, and we have some word problems and we have some radical equations, and a couple of them have tutorial videos available. Thanks for your attention today. I know that was a lot.